Alright, so for this first question we have use Euler's method with step size 0.2 to estimate y of 1, where y of x is the solution of the initial value problem y prime equals negative 2x plus y to the power of 2, and then the initial condition being y of 0 equaling negative 1. So the first thing that I like to do is write down what they gave us. So we know that our step size will be 0.2. So we can write that as h being 0.2. And then our initial condition is y of 0 equaling negative 1. Next, I'm going to draw a table. So the first column will have n. The next column is going to have x sub n, and then the last one is going to have y sub n. So let me go ahead and complete this table here real fast. Just like that. So when we look at the initial condition, this will be our first x sub n, and then this will be our first x sub n. So we could go ahead and plot 0 right here, and then negative 1 right over here. And then this will be our n equals 0. So now you might be wondering, how many steps do we need to take in order to make the approximation of y of 1? Well, that will be determined with both the x sub n column as well as the step size of 0.2. So at step 0, we have x sub n as 0. So we need to get from 0 all the way to 1, because here we have x being 1. That's when we need to make the approximation. So next we need to look at our step size. We know that for every step we move forward, we are going to move 0.2 in the x direction. So now all you have to do is start at 0 and then count all the way to 1 using 0.2 intervals. So let's go back to our column of x sub n. So we have 0 here, the next step will be 0.2, then 0.4, then 0.6, 0.8, and then finally we'll get to 1.0. So then we're going to have 1, 2, 3, 4, and 5 steps in order to get our approximation. So at this point, everything is set up for us. All we need now is the equation. So this is the equation for Euler's method. So we're going to have y n plus 1 equaling y sub n plus h multiplied by f prime of x sub n comma y sub n. So we began at n equals 0, and as the equation has it, it's going to be y n plus 1. So y 0 plus 1. So now we're going to move to find y sub n when n is 1. So let's go ahead and begin plugging in numbers. So now we're going to be figuring out y sub 1, which is right over here. So y sub 1 is going to equal y sub 0 plus h multiplied by f prime of x sub 0 comma y sub 0. So now let's plug in our values. So y sub 1 is going to equal y sub 0, which we have, it is negative 1, and then plus h is our step size, which is 0.2, multiplied by f prime of x sub 0, which is 0, comma x sub 0, which is negative 1. And before I move on, I am going to go ahead and solve for f prime before we do anything. So f prime of 0, negative 1, will be equal to, remember this is our x and this is our y. So we need to plug both of these into our first equation. So the original equation was y prime equals negative 2x plus y squared. So we're going to have negative 2 multiplied by x, which is 0, and then plus, it's y to the power of 2. Y is negative 1, and it's going to be squared. So this will give us 2 times 0, which is 0, and then negative 1 times negative 1 is just simply 1. So our answer is 1. So now let's go back to Euler's method. So y sub 1 will equal negative 1 plus 0.2 multiplied by 1. So now you see that instead of writing f prime of all of this, I just ended up writing it as a 1 because that's what f prime equals. So now we're going to have y sub 1 equaling negative 1 plus 0.2. So y sub 1 will equal negative 0.8. So we can go ahead and write that under our y sub n for n equals 1. So negative 0.8. So now let me go ahead and delete this stuff and move on to n equals 2. So now we are right here at n equals 1. So now when we look at the equation, it's going to be y n plus 1. We are at 1, so 1 plus 1 is 2. So y sub 2 will equal y sub n, which is what we're at, so 1, plus h multiplied by f prime of x sub n, and then y sub n. So now let's do the same exact thing that we did last time. So instead of writing n, I'm going to simply write 1, because we are looking at n equals 1. I just forgot to write 1 instead of n for some reason. So y sub 2 is what we're looking for. Y sub 1 is right here. It's what we just got. It's negative 0.8, and then plus the step size of 0.2 multiplied by f prime of x sub 1, which is 0.2, comma x sub 1, y sub 1 I mean, which is negative 0.8. Something interesting is that the negative 0.8 matches in both of these areas. That's because they're using the same exact y sub 1. So here we have y sub 1 and y sub 1. So they also match when we put in the number. So like before, I am going to solve for the f prime really fast. So we have f prime of 0.2, negative 0.8. So this is going to equal, remember that this is our x and this is our y. So we're going to have negative 2 multiplied by x, which is 0.2, plus y squared. Y is negative 0.8, and that's going to be squared. If you're wondering where I'm plugging these numbers, I am simply plugging them into our equation right over here. It's the y prime equation that they gave to us. So whatever x sub n and y sub n are, I end up just plugging them into this in this step. And if you wanted to, you could solve the f prime as you move along with the problem, but I just like to solve it first here, so then I could just plug in a single number like we did last time. It just speeds things up a little bit more. So then this is going to equal 0.24. So once again, let's go back to Euler's method. So y sub 2 will equal negative 0.8 plus 0.2 multiplied by 0.24. And once you plug that into a calculator, you're going to get out negative 0.752. And now we can go ahead and write that down under our y sub n column. So when our n is 2, our y will be negative 0.752. And then let me go ahead and remove these things and move on to n equals 3. So now we're solving for y sub 3, and it's going to equal y sub 2 plus h multiplied by f, x sub 2, y sub 2. So y sub 3 is going to equal y sub 2, which is negative 0.752, plus our step size h, 0.2, multiplied by f prime, x sub 2, y sub 2. So then let's work on f prime. So f prime of x sub 2, which is 0.4, and then y sub 2, which is negative 0.752, will equal negative 2 multiplied by 0.4 plus y squared, and y is negative 0.752, and then squared. And then this will equal negative 0.234. So now let's move back to Euler's equation. So y sub 3 will equal negative 0.752 plus 0.2 multiplied by negative 0.234. So now our answer will be negative 0.79 So let's go ahead and write that down. So negative 0.798. And let me go ahead and delete these and move on to step 4. So y sub 4 will equal y sub 3 plus h times f prime of x sub 3 comma y sub 3. So now y sub 4 is going to equal y sub 3, which is negative 0.798 plus 0.2, or step size, multiplied by f prime of x sub 3, which is 0.6, and then y sub 3, which is negative 0.798. And then once again, let's solve for f prime right over here. So f prime of 0.6 comma negative 0.798 will equal negative 2x, and x is 0.6, plus y squared, and y is negative 0.798, and then squared. And now this will be approximately negative 0.561. And now let's go back to Euler's method. So y sub 4 will equal negative 0.798 plus 0.2 multiplied by negative 0.561. And now this will be approximately negative 0.911. And then that can go under our y sub n when n is 4. So negative 0.911. And then once again, let me just get rid of all of these. So now finally, y sub 5 will equal y sub 4 plus h multiplied by f prime x sub 4 y sub 4. So y sub 5 will equal y sub 4, which is negative 0.911 plus h 0.2 multiplied by f prime of x sub 4, which is 0.8, and then y sub 4, which is negative 0.911. Then we're going to move to solving the f prime really fast, right over here. So f prime of 0.8 negative 0.911 will equal negative 2 times x, which is 0.8, plus y squared, and y is negative 0.911. And now this will equal negative 0.769. And then back to Euler's, we're going to have y sub 5 equaling negative 0.911 plus 0.2 multiplied by negative 0.769. And then that'll equal negative 1.065. So we can go ahead and write that down right over here, negative 1.065. And now we can answer our question. So y, when x equals 1, which is right over here, is going to be equal to negative 1.065. And there we go. That's your answer, and then here it is once again. And now you can see that we took 5 steps, 1, 2, 3, 4, and then 5. And then after 5 steps, we were able to estimate what y would be when x equals 1 without actually solving the differential equation. And now I want to talk a little bit about what Euler's equation is actually doing. So let me go ahead and just draw a graph really fast. So let's say that this graph here is the right side of y equals x squared. And now let's just plot a random point along this graph. Let's say right here. So if you want to do a tangent line approximation, it would look somewhat like this. So now you see that the tangent line approximation is really good at approximating as long as it's really close to the point where we plotted it originally. But you also see that as we move further and further away from the initial point, we start to lose track of where we are. So you see that these 2 points are a little bit far away in comparison to the initial, which is right on the dot right here. And if you were to keep moving on and on, then that effect will just be made more clear. So eventually this x squared will keep going as well. And then there's going to be a point where the difference is like right here and right here, which is a pretty big difference. And at that point, you shouldn't even use that tangent line approximation to approximate anything. So now let's talk a little bit about why Euler's method is a better method of approximation than the tangent line approximation. So once again, I'm just going to plot a random point along the graph again. You can think of Euler's approximation like the tangent line approximation, but with course correction. And what I mean by that is that at every h value that we move along the x-axis, we will adjust our slope, and because of that, we will get a better approximation than the tangent line approximation, which does not adjust its slope as we go on. So if we look at what that looks like, we can move a little bit forward and then stop right here. So you can consider the distance that we traveled in x here, the step size, which is h. And as we move from step to step, we are going to slightly adjust our slope. So now the next point could be like right over here, and then it's going to connect there. The next step will be up here. It's just going to follow the line of x squared, and then the next one will be maybe over here, and just like that. So you can see that every time we move a step, this will be another h, and then this will be another h. So every time we do that, we adjust the slope. And it's for that reason that it is a better approximation method than simply using a tangent line. This method is way more accurate, and it's pretty cool. And finally, I just want to quickly cover some relationships. So once again, I kind of plotted a random point along the graph of x squared. And this dot is going to have an x value, which we can call x sub n. And it's also going to have a y value, which is y sub n. So back when we were doing that practice problem, we were moving h amount in the x direction. So I'm going to demonstrate what that looks like here. So we start at a specific x value, and then we move ahead one step, which is h. And then we're going to move up a little bit as well. Let's say right here. The new y value is going to be called yn plus 1, similar to the equation. So let me just delete this really fast, and I am actually going to bring up the equation really quick. So the equation was yn plus 1 equals y sub n plus h times f prime of x sub n plus y sub n. And then let me rearrange it a little bit. And yeah, I did forget my 1 here for some reason. So let me rewrite this as yn plus 1 minus y sub n will equal h times f prime of x sub n plus y sub n. And if you're wondering what I did, I just simply moved y sub n over to the left side. So you subtract y sub n from both sides, and then you get yn plus 1 minus y sub n equals h f prime, and then that argument. And you might be wondering why I did that. And the reason is to show how much we went up. So if you haven't noticed already, we have yn plus 1 and yn plus 1. And then it's being subtracted by y sub n. And y sub n is also right here. Therefore, if we subtract yn plus 1 minus y sub n, we will get the difference in y right here, which is also the same as the difference there. So as it turns out, what we have on the right side is the amount that we go up right here. And that was a really bad arrow, but you get the point right there. So let me go ahead and just write it down just so we have it on record. So we're going to have h, the step size. That is a really bad h again, so I don't know what I'm doing. So h times f prime x sub n plus y sub n. So this will be the difference between yn plus 1 and y sub n. And of course, this will give us a new point around right here. And then we're also going to have a new slope. So the slope right here, we can calculate like any other slope, rise over run. So this portion here will be our rise. That is how much we're going up on the y-axis. So this will be our rise. So we're going to have h and then times f prime of x sub n and y sub n. And I didn't even notice this is not supposed to be a plus, just a comma. Same over here. I don't know why I did that, but yeah, comma and comma. And then this will be divided by the run. And the run is right here. It's how much we moved and traveled on the x-axis. So then it's going to be divided by h. So the slope m will be equal to this. And we can actually cancel out the h. So this ends up being simply f prime x sub n, y sub n. So this is what's going to determine our slope every single time. And that'll be it for this video. Thanks for watching, and I hope you learned something new.